Hello out there.
Hello.
I'm looking at the delightful John Swain right in my face here. How you
As soon
doing,
as you
sir?
knew
How's
there was
everybody?
somebody here.
Yeah. Well, it's funny. I'm about to type this in the chat when people jump in, but I'm going to have a rule just for tonight only. Well, because it only matters for tonight only is I want no basketball score updates given. I want no one in the comments, and I'm going to have to make that because I've got it on record. I haven't watched any of it. I know it started 45 minutes ago, so I know nothing. I want to know nothing. You can give me all the hockey scores you want. I don't care. Speaking of hockey, I was a little disappointed. I stayed up. I can't believe it. Mr. Frederickson's old college team in North Dakota, 5 overtime hockey game, and they lost 3-2. As you all know the sport of hockey better than I do, overtime's pretty rough in hockey because you got the full intermission between every overtime period. So it makes it a long game with that many overtimes. But dang it, they lost. That's all right. So I'm recording. I'm gonna put that in the chat so people jump in the show here that, I don't want to, don't tell me anything. I'd appreciate that greatly. Other than that, we're going to proceed as normal. So let's see what we got going on here. All right, let's get the notes up for today. And I'll share the screen here in a second. I didn't know what kind of crowd we'll have today, whatever. I mean, obviously, because you guys could be watching the game while you're looking at this too. That's what, no one's stopping. I don't, because I don't want to start yelling profanities into the recording or anything like that. So it's best if I'm not keeping an eye on it while I'm trying to cover this stuff. Might not go well. All right, so I remember we did the discrete distributions and specifically the binomial. Today we start the normal distribution. All right, now I'll come back over here. All right, whatever. Let's see. Where? Okay. Okay, let's share that. I don't need this, whatever that is. But I do need our notes to come up here, so. Okay, that's the part. Yeah, okay. There we go. That's what we're going to be doing the first part of the class. Let me see if I can navigate my way over here real quick just to make a chat thing about the just so when people might have to come in. Please don't update me on the score of the Houston game. Since I'm watching it after class. All right. All righty. Let's put that in there so someone jumps in. So that's pretty funny that the administrative course of business here starts out with a basketball game, but hey, it's a big deal for our little program. Speaking of which, class-wise, let me get into Blackboard here for a minute. I guess we have to start thinking about the next exam pretty soon. I know that sounds exciting. Let's see. Right. I was trying to remember off the top of my head where probably after these 3 parts of the normal distribution, that's probably it. Maybe one more. We'll definitely get those 2 sections done today. Let me take a look at my little course content here and all right. Lecture notes. All right. Yeah, so it's the three parts of this normal distribution is where we'll conclude the exam. All right, that being said, but we can talk about, when we're finished today, think about when we're going to have it for sure. We can go ahead and set it up just so you can start kind of making plans and whatever. The area will run just like it did. Everything will be exactly the same as it was last time, as far as the structure and everything. So that won't change. We'll just need some dates and whatnot. So, all right, now we're going to, this normal distribution. Now we talked about last week, discrete and continuous distributions. Now we're getting into continuous distributions. Now there are several, like I mentioned last week, there are several kinds of discrete distributions. We studied the most important one, which is the binomial, and the same thing holds true here. There are several continuous probability distributions, but the most important one by far is the normal distribution. So that's a more advanced math probability class could go into some of those other ones, but we don't need to. And anything that would be used business related would be based on this normal distribution, not really anything else. Highly unlikely. So let's continue. So we're going to have to kind of get the idea of how continuous distributions work at the same time we talk about normal distributions. We used to do one called the uniform. They took that out. The uniform is actually pretty easy. I might just show it to you real briefly if we have time, but because how it kind of relates to the area here. We did do uniform for a bit. I didn't see the need to bring it back since it wasn't required, but it's actually easier than this. Right, so normal distribution, normal curve, bell curve. And why this is so important is that many data sets will fall into this type of distribution. Now let's look at some of the properties. Some are more key than others. The first one, mean, median, and mode are equal. Okay, that's fine. That's not super important. The main thing is that on these normal curve graphs is that the mean, and we're using the population mean here, always lies right in the middle of the graph. And we've already talked a little bit about the normal, when we did the empirical distribution. We're just taking it to another level now. This curve is bell-shaped and symmetric about the mean. Essentially, bell shape we talked about before. It means if you fold it over, it matches on the other side. Now, in reality, if you have, let me sketch something out here. That's to be what we call perfectly normal. But if a data set or something look like, actually, let's bring up something here. You can be kind of close to normal and still kind of work with it and treat it as normal. In other words, I guess it's recovering some old note. Might be something from last week or something. I don't know. Yeah. Oh, yeah. Well, I just go down below this or just go to new page. So let's say if the distribution kind of look maybe I don't know. Okay, something like that. We could probably still, work with that as being a normal distribution if we were trying to make claims about the data set. So these definitions are kind of based as if it's perfectly normal. That's the way we kind of work with it. But you could still theoretically use it even if it wasn't quite like that. Now, the total curve is bell-shaped and symmetric about the mean, okay? The total area under the normal curve is equal to 1. Area, let's talk about why that's important. Is because area is how we're going to measure the probability. Now, we're going to have charts that help do this and stuff. And it's sort of similar to the idea of the last time, the sum of all probabilities in a discrete distribution equal to 1. Well, this is different because it's continuous. You can't add individual probabilities. So now if we're talking about this idea here, let's say if we're going to, we'll talk about this more in here in a little bit. Let's say probability between 2 and 4 or something. We're now talking all real numbers. It doesn't really matter whether those equals are there or not. So it has to be measured in a continuous type way. So we use chunks of area. Now, like I said, I'm just going to do this real quick. I mean, I don't worry about, I could make this look a little better. Let's see. It can take on different shapes, but the uniform distribution is a rectangle distribution. And let's say if this was like 20 to 80, and you wanted to measure, let's say you wanted to find the probability between, let's say, 60 and 80. Now I'm just kind of estimating where this would go. You would be finding that chunk of area right there, which is pretty easy on a uniform, because being a rectangular distribution, we know it's the total area of one would be width times height. Then you would just measure width times height of what you wanted, and that would be your probability. Now the normal, so that's the uniform. I didn't write that down there, but once again, you're not tested, or nor do you need to know any of this. But it's a real easy one, because it's measured on rectangles. Well, that's what we're going to need charts on this, either charts or some serious calculus, which we're not going to do the serious calculus, but because the way you find area under curves that aren't simple things, geometric things like rectangles and stuff like that, we don't need calculus. But for things like this, that's how you find area. Calculus finds area under the curve. Well, we're not going to need calculus. Thank goodness. We're just, we're going to have some charts and be able to sort of do it that way, where some areas are kind of already pre-calculated and stuff. So, all right. Now, this last property is not super critical. In other words, that graph actually never touches the x-axis. It's not critical that you know that. I would never try to trick you with that on a test or anything, but the idea is it gets so infinitely close to the x-axis, it might as well be touching it, but it's not really. So I guess when you say that total area is 1, that kind of means between negative infinity and infinity, but you really don't have to go that far out, because it's getting so microscopically close. Okay. And that's okay. I just sort of talked about this. The area is important, because area is what measures probability for these curves. Okay. Now let's come down here and look at this. Now this is, you don't have to worry about this specifically. That's kind of has to do with the empirical rule that we learned, but don't worry about this. It's kind of interesting though, is that so it's kind of showing between plus and minus 1, plus and minus 2, and plus and minus 3. Well, we're going to do more than just that. Obviously, if we were just doing 1, 2, and 3, we would just keep using the empirical rule. But we might want to know the area between 1.35 standard deviations below the mean and 1.58 above the mean. So that takes out the empirical rule. That's the end of that. So. But this is just showing for 1, 2, and 3. But it's kind of interesting. I don't know why the empirical rule just doesn't do this, but so you see it's got this 34.1 and 34.1. And most all books do it this way. It seems like the empirical rule was 68% between plus and minus 1 standard deviation. 68.2 would have actually been a little more accurate if they used 68.2. So I don't know why they don't, but all books just use 68. Same thing with the next one, where we said between 2 standard deviations below, we use 95% from the empirical rule. 95.4 is a little more accurate, is a little better. Now the last one matches kind of right on the money, 99.7 between 3 standard deviations. But don't worry about these little sections here. I mean, we're not going to need to worry about that. Now, what I'm showing you here, and I got an example of that below, is when we're just kind of rough sketching normal curves, we don't have to really worry about how skinny they are, how flat they are. But I just wanted to mention this just from a conceptual standpoint. What changes the shape on these graphs is the standard deviation. Like these two graphs, both have the same mean, because like I said a little while ago, the mean is always a number. Why am I using my mouse when I could just use my stylus? Sorry, I can do a little better job. But the mean is always right in the middle. So I kind of messed up here, but you get the idea. 52. Okay, right in the middle, 52. But the shape changes is that the larger the standard deviation, the flatter the graph gets. And that makes sense because if it has a larger standard deviation, values are going to be spread out across a broader range of numbers. So it makes sense that it would flatten out. And then it gets skinnier and taller when it's a smaller standard deviation because the values are closer to the mean. But the one thing that both these graphs share is they both share the property that the total area under them is equal to exactly 1, whether it's tall and thin or short and wide. It still has to be a total area of 1. So, okay, that's not hugely critical, but I could have a question on test and show you 4 graphs and just say which one has the largest standard deviation, and it would literally be the one that was the flattest of the 4. If you knew nothing else about the graph, that's all you'd have to know is which one's the flattest. All right. Just the opposite then, which one's the narrowest, the smallest standard deviation. It'd be the tallest and the thinnest one. Now look at this. Thank goodness we don't need this, but this, anytime you have a graph has to be based on some sort of equation. It doesn't just magically appear from nowhere. There has to be some equation that generates the y values for all the x values. Now we don't actually need this, but I always like to show people this, just, curiosity or whatever. It's quite the doozy of the equation there, isn't it? I mean, it's got everything. It's got your standard deviation. It's got everything. It's got pi. It's got that exponential number e in it. And it's got it all, doesn't it? But that's the actual equation that would draw that graph, which good news is. I did a couple of them in the calculator just to show you, but you are absolutely not required to do that. So it's like I said, if you know what the standard deviation, if it's smaller, whatever the mean is that you put in there for mu, that will be the center of the graph. And of course, the standard deviation's in the equation twice, and that's going to decide how skinny it gets. And this is just, you don't have to know this either. I'm just going to tell you. But one reason is that it never touches the x-axis is because e raised to a negative power is 1 over e raised to a positive power, which can get very, very, very small. But 1 over a number can never be 0. Although if you did take a calculus class, you can learn that the idea of a limit makes it approach 0, but 1 divided by something can never exactly equal 0, but be very close. All right, so the good news, you don't need that scary, ugly equation. Now, these 3 graphs, which one has the greatest mean? Okay, the greatest mean would be literally dictated by which one is farthest to the right, because that means it would have the largest center number. That's how you would dictate this as the position. Now, we know the standard deviation idea. We talked about that, but I hadn't mentioned the mean thing here. So B would have the largest mean because it's farther to the right. A and C have the same center. It's a tied mean. But which one has the greatest or largest standard deviation? Would be the flattest of the 3 graphs. So it would definitely be C. The smallest standard deviation would clearly be A, because it's the tallest and narrowest of them. So that's not too bad. Okay. All right, once I did this in the calculator. Don't worry about this, but I put in these values. And then you see the Y1 that with the smaller standard deviation, see that graph was the taller and narrow one. I use that ugly equation I just showed you right there. Not that you ever have to do this, but one thing that's tricky about graphing this is you got to be careful with your how you set your windows on this. Because if I remember correctly, I think the x-axis, yeah, they go by tens. For sure they go by tens. Because you see that second tick mark right there, that 2 would represent a mean of 20. But I think that y value right there is like 0.1 or something like that. Because keep in mind is that the total area of that curve has to be 1. So you can't, if you just let it default, it's going to be such a small graph, you're probably not even going to see it. If you let the windows kind of be normal or whatever, it'd be hard to really see. But okay, that's not important. But But it's funny sometimes when people are doing stuff in calculators, the rare times they have these situations. I can't see my graph. What's wrong? You had to finagle the window to make it work right. But you never need to do this, so don't worry about it. But I'm saying if somebody out there was just curious, and wanted to do it, yeah, you'd have to play around to really get the screen in view there. So, all right. Now, calculating probabilities from a normal distribution, there are always going to be inequalities. Whenever we did the discrete, and when I say discrete, that includes the binomial because it is a discrete. So either one of those last two sections, they could have been done as inequalities, or they could have been done just as the probability of x equals something. But in a normal distribution, it's, you could possibly approximate it. We're not worried about it, but there's really no idea of saying x equals something because you're trying to measure a continuous range of numbers. Measuring one number would have no width, on the graph, I'm talking about width and height or whatever, has no width. So in theory, it's going to be basically zero. I usually don't put that generally on a test, but this could come up in a homework problem. So anytime we're doing a normal distribution problem and it just says whatever, okay, you found this probability, you find that probability. I want to say that's in there because that does sound familiar. And then it says, okay, find the probability that x equals 20. For these problems, for the normal distribution, you just put in 0, hit enter, get your check mark, and move on. You don't have to even put any more effort into it than just typing in a 0. But that's only for this. That is not true for the discretes. Those would be for binomial, you would have to just calculate that by whatever means. Okay. Now, here's another difference between these continuous distributions, specifically the normal, versus the discrete distributions. Now, the equality symbol below the inequality symbol makes no difference here. It still does before, like when we did. We're not changing that rule. We're just saying now that doesn't matter whether it has an equal there or below it or not, because it's going to be calculated the same way. And I sort of have I could draw a graph, but I don't think I need to. We can just look at this written explanation. Because like in a binomial, if we say find the probability that x is less than 3, that automatically means it jumps down to 2. No questions asked. It would be, for binomial, it would just be 2, 1, 0. Actually, I think I will do a picture. But in a continuous distribution, less than 3 really means 2.99999, blah, blah, blah. Yeah, I think I will sketch a real quick picture. Okay, well, I don't have to draw a normal curve. I'll just use a pre-done one here, but of course the 3 can be anywhere. I mean, it depends on the mean. I can put it on the left side of the graph. Yeah, let's say that I'll make the mean be 5 here. Remember, the mean's always the center number. Now, I'll come up with something. Obviously, this was like a traditional number line. 3 has to be to the left of it. Now, I'm going to draw a dashed line here. I have the concept of like asymptotes or whatever. This is not an asymptote per se, but I mean, you kind of know, mean you can't touch it. It's like an invisible wall there. Well, I'm going to draw this just somewhere right about here. It doesn't really matter, but. So what I'm saying is whether that's dashed where you can't touch it or it's solid where you can, if you're calculating the area, and if that area is getting so infinitely close to that dashed line, so close, whether it touches it or not, it's producing the same area basically. So it really doesn't matter that it touches that because it's kind of getting infinitely close to it. So that's why it does not matter for the normal distribution whether we have the equals or not. So you're going to have to sort of get those ideas kind of adjusted, changing a little bit. We're not changing what we already learned in respect to what we learned. We're just doing this different. So you see now I have how they could be equal, or it's the same calculation whether it has the equal or not. So here's an example. I'm using a binomial specifically. So the difference between, if you say between 12 and 14 with no equals, so that would just mean 13. 12 and 14 with equals. Of course, remember, you can have equals at just one end or the other. when we did the discrete section, we covered that. But equal at both ends, 12, 13, 14 would include both. But I'm telling you here, for the normal distribution, these are the same thing. Now, I talked about we're going to have a chart, a table we're going to use. Might as well go ahead and, I guess I can bring that up while I'm in Blackboard. Okay, let's see. Yeah, if we were doing in-person exams, this is where I would always interject with a comment. All charts and tables will be provided for the exam, but that doesn't apply to you. Because obviously, you can, you'll be able to have complete access to it. So people will be worried about, do they have to bring the chart or do I provide it? And that doesn't matter. Obviously, in our format, it'll be right in front of you. So, all right, just kind of keep this up and ready there. So, all right. So we'll come back to this in a minute, but I wanted to have that ready because that's going to be our new lookup chart for this stuff. All right. Okay, now when I talk about a lookup chart, the idea of this is thinking, if somebody might think of this and go, well, wait a minute here. It's sort of like the idea with the binomial. We just use a limited set of tables for those, but theoretically you could have infinite binomial tables. Same thing here. This is totally different than the binomial, because you're going to see here in a minute why we only need one table for this. Because you could have a data set that has just unlimited possible means and unlimited possible standard deviations. So it seemed like it would just take a giant library of tables to do this. For example, you might have one data set that has a mean of 60 and standard deviation 12, mean of 120, standard deviation 30, mean of 250, standard deviation 50. And you think, geez, I mean, do I have to have a bunch of references to look this stuff up to find these areas? And these are all based, if we just call random, if they're just some random variable x, which you assume any problem would just be random variable x. Now, here's the fun part. We have a beautiful and magical way to convert any normal distribution to a specific singular normal distribution, which is what our chart is based off. So we can convert anything into one measurement where we can use one chart. So that's just utterly, utterly fantastic that we can do that. And it's something you've seen before. Not doing this, but remember that thing we had called the z-score? That was on the first exam. We hadn't seen it this unit yet, but the z-score. Now, so those are all the distributions I gave up here are just random normal distributions, whatever. Only one specific normal distribution has a name. It's not a fancy name. It's called the standard normal distribution. The standard normal distribution is only one specific normal distribution. It has to have a mean of 0, and the standard deviation will be 1. Anything that doesn't satisfy those guidelines is just a regular normal distribution, not the standard normal distribution, because that's what we're going to be converting to be able to use our chart. And to convert it, it's using, right over here to the right, it's using that z-score formula that we've already seen before, where you take whatever your data value is, you subtract your mean, and divide by the standard deviation. So we take our problem, if it's not already a z, so we use random variable z whenever we're talking about the standard normal distribution. It would be x for anything else. All right, so I'm just saying, let's take two different x values. So let's say we have a normal distribution with mean 48, standard deviation 8. We're converting it to a value for z. And let's see what we get. And the idea of what the z, let me remind you kind of what that means, is it tells you that the number of standard deviations that a value X is away from the mean. And when I say away from the mean, that means if it's a positive number, that would be above the mean. A negative number would be below the mean. And if the Z is 0, that means the X value was the mean itself. So like if I put 48 in here for X, I'm going to get 0 because 48 minus 48 is 0. All right, so let's see, we take 60 minus 48 and divide by 8, we get 1.5. So that's telling me 60 would be 1.5 standard deviations above the mean. And then for 32, we take 32 minus 48 divided by 8, we get negative 2. That means 32 would be 2 standard deviations below the mean. All right, fun stuff. Now, let's talk about how we use this normal table. Now, when we're calculating normal probabilities, we're pretty much looking at, there's one graphical example, it's a little bit different, I'll show you, but let's just say, 99% of the time plus, we'd only be interested in 3 things: less than, greater than, or between 2 numbers. That's what we're going to be interested in doing. Now, however, the chart is strictly based on less than. So we're going to have to see how to use this chart. And I'll also show you this in the calculator. You can decide what you want to do. I don't know. You can decide. I'm not sure if you consider the calculator to be it will be a benefit in some cases, but I gotta show you how to read the chart, because it would be unfair not to, because somebody wasn't using a fancy calculator. All right. But then, I'll give you that perspective too. So let's see. Okay, I mentioned where it's located. We just brought up the chart from the notes there. So from Blackboard. Okay. But the chart is based on left. And let me go back to the chart here. All right. Where is the chart? Oh, here. Okay, here we go. Now, notice this chart kind of stops here at about negative 3.49 and also stops at positive. Okay, that's, yeah, you can have Z's lower than that. But, since 99.7% of the data, by definition, on the normal curve, 99.7 is between negative 3 and 3. You're kind of looking at outliers, and anything farther than that. I guess point being is let's say if it was negative 5, and you could pretty much just say the area below negative 0.5 is, you can say 0, and that's good enough. It's not technically 0, but sometimes if a number's so small enough, you could pretty much just say it's 0. I thought 349 actually should be 0.0001, but that's okay. If you do it in the calculator, you might get slightly different answers, but I think that the homework will be, it won't affect you on an exam, because I never put answers that close together, but homework I think is pretty good. I've checked this out before with doing them via chart versus calculator. Even if they're off on that last decimal place, it seems to accept it. But yeah, they just stop at negative 349. Most normal tables do, because it's almost like pointless to go any farther out than that, really, because that's when you're kind of out in the real flat part of the graph. But notice the picture here of the graph of the shading, that it's shading it to the left. So you got negative side, and then this chart has 2 pages. It's got a positive side, and so it just picks some random Z to the right and the middle. Because we're using the standard normal table, that by definition, that means 0 is in the middle of this thing. 0 is right in the middle of that graph, because that's your mean. And they're showing, so it's going to the left. So anytime we're looking for things to the left, it'll be straight off this table. But what we're going to have to do is learn how to manipulate this, though, and we can. It's just one table, but we can do left, right, between, all off of this one table. So we'll be able to manipulate it to do that. Okay. Now, keep in mind, these areas that we're finding are probabilities. They are probabilities. because a normal curve area equals probability, or any continuous distribution. Even that uniform I showed you, the area was the probability. Let's see. They have to be answers between 0 and 1 still, so that's something to keep in mind. Any answer you come up with is not between 0 and 1. See, values for Z can be negative, but probabilities can't be negative. Those areas are both positive numbers smaller than 1. Okay, so let's try this out just reading the table. Like I said, I'll show you both calculator and chart. But we'll do chart first. Find the area to the left of a z-score of negative 2.19. Another reason sometimes the calculator might be a little different answer when you do certain stuff sometimes is because it can do these calculations. It shows, it doesn't just show 4 decimal places or whatever. It kind of does it a little more precisely, but it doesn't necessarily mean we need that, but so it can throw it off sometimes. But it shouldn't make you miss a problem or anything. Now here's how you read this. So what you do is to find up to the first decimal place, you go down the first column. Now, of course, whether it's negative or positive, ours was negative 2.19, I believe. So obviously that means I want to work with the negative part of the chart. So you go down, you find then the row that you're looking for. So there's, can I get all this? Yeah, okay. So I'm just going to highlight that right there. Hopefully we can zoom in a little bit there. There we go. So there's your negative 2.1. Now across the top, that's what gives you the second decimal place. So the second decimal place was 9. So I would choose the last column, which is the 0.09. So it's essentially where row meets column. So it'd be right here. So once again, I'll show you. So you see that's in the negative 2.1 row, and it's in the 0.09 column. They meet right there. So it would be 0.0143. And I think I did actually snip that part of the chart. Yeah, I did. I just wanted to do it actually showing you how I did it, but there's a snipped out part of the chart right there where I circled the row and I circled the column. And so let me just tell you real quick, because we're going to be putting these into calculations. And the first part of part 1, we're just kind of learning how to, read the graph and do kind of stuff. The next one, we'll start calculating normal probabilities. But let me just sort of translate this area statement into a probability statement, just a general probability statement. So by finding that 0.0143, okay, what did that mean in the scheme of things? All right, I'll tell you. If you took a data set and you said, what's the probability that I pull out a value at random that's negative 2.19 standard deviations below the mean or less than that? In other words, that's the highest it would be is negative 2.19 or below. And then if you made this a percentage, you would say you got a 1.43% chance that you're going to pick one that far below the mean. That's sort of how that translates into some usable statement. Okay, now back to just reading the chart. 1.27 to the left, and everything's got to be left right now until we talk about how to manipulate. So when it's to the left, which to the left will mean less than when we're doing probability calculations. Back to the chart. Now it was 1.27, so that probably means I need to be on the positive side of the chart. Here's 1.2. That's my row. And then I go over to the 0.07 column. So if you look at that number I've got highlighted, it's in the 1.2 row and it's in the 0.07 column. They match right there. And it's 0.98980. Yeah, so that's not too bad. Now, how we manipulate it's a little bit different, for the other stuff we need, but just the basic reading of it's not too bad. Do I have that? Yeah, so I have that one kind of circled right here also. 1.2 meets 0.07 to make 1.27, and then we have 8980. And I'll say so an 89.8% chance that your value you picked is either no higher than 1.2 standard deviations above the mean. So it can be that high or any number lower than that. So obviously that's a pretty high probability that you would satisfy that requirement if you just took a value out of the data set at random. Now, calculator. Now let me show you how to do this. You have to be real, comfortable with, I mean, not, or at least if you're going to do it, get comfortable with the concept, of inequality. Is that, inequality notation that you learned back in algebra? So you have to be aware that, so let's say this one's doing the negative 2.19. So if you're saying, I'll just write it up here and then I can erase it. So, oh, I'm sorry, that's Z right now. Later on it'll be X and we'll turn it to Z. Well, whatever, I should label that correctly, but it won't make a difference what I write here. So we have to understand that means this in interval notation. That's very important because how we enter this in the calculator. That's why we got to know that correct order. Now there's a normal PDF and a normal CDF. There's two of those also for the binomial we did last week. We don't need the normal PDF for anything here. We'd always use CDF. We don't even need that. Normal CDF. Now, so what you have to, so you see I have it written down here below the calculator box. Actually, I've been doing this a different way. And down here, I'll show you. The negative 100 is still okay. But I'm going to show you this negative 1e to the 99. I used to just kind of do it with negative 100. You'll see why, because of the newer. This is when I just had to type it in. I just used negative 100. And you might be thinking, well, negative 100 doesn't sound very small. But it is for a Z value, because like we talked about, if you're between negative 3 and 3, that's 99.7% of the values. Hey, I need to change that box and put this 1e thing in there. Using this, but that's okay. I've already done it now, so I'll show it to you. But if you're, normal CDF on an 83 or the older 84, they'll pop up and you enter those values. It's going to be a different looking prompt here, on the newer calculators, which I'll show you that right now. So when you do normal CDF, it's probably just going to pop open with on 83 for sure. It'll just have a left parentheses. But going back to my story, is negative 100 on a Z distribution is more than sufficient to represent negative infinity. But in general, if we were using X values, I would not say that. That's why I might just start using this 1E99 for all purposes here. So let me warm up the calculator. And I'll just talk about this for a second. That negative 1e to the 99, that's like negative 1 to the times 10 to the 99 with just a bunch of zeros in front of it. So that's a really tiny number. Because the newer calculators default with that negative 1e to the 99 already in there. So there'd be no need to change it to negative 100. But you can, if you're just using a TI-83, you can use negative 100. But if you want to get used to, even with the TI 83, if you want to get used to using the negative 1e to the 99, and we'll talk about the positive 1e to the 99, we got to know both. All right, here we go. So it's the second one, normal CDF. So it's the same second bars distribution. Yeah, I mentioned second bars, same command we used last week to get to the binomial. Remember, the binomial is down a bit, down a few items. This one's right near the top. We're actually going to be using inverse norm today too. No, probably next week for inverse norm. But we will be using it. Yeah, you see that starts out with that lower being -1e to the 99. So we can leave it, but I'm just telling you -100 would work. And I'll put in upper minus 2.19. So it's lower to upper, just like you would write it in interval notation. And this is fine. 0 and 1 are already. Now, if you're using 83, you don't have to put the 0 and 1 in there because that's what the default is. So you don't have to, you might be wondering, do I have to type in the 0 and the 1? No. Watch what comes out of here. So that's one way to look at the way they do these things a lot of times, is what you see that comes out of here. Oh, I'm sorry, I was wrong. It did put the 0 and the 1 in there. But I'm telling you, if you got an 83 and you're playing around with it, well, notice, look at my notes. Okay, I'm going to hit enter here to show you. And there it is, 01426. Notice that I don't have the 0 and the 1 entered in this calculator box right there. Okay, that's because that was the default. So whether it was there or not, oh, here, and I'm showing you, and I just showed it again down here without the 0 and the 1. That looks like on this one I intentionally probably backed up. It won't come out that way. I must have arrowed back over to get rid of them. All right. Now this one was for the other one. The one, so was it 0143? That's what we got from the chart, wasn't it? Yeah, 0143. I'm going to go ahead and erase this. And let's see, so the 1.278980. So we could do that one real easily, because if I go second, bars, normal CDF, and I can put 1.27. So anything that's less than must, if you're using this, you must start out with either the -100 or the -1e to the 99. And there it is, 8980. So you can do it this way if you want to. It'd be totally up to you. You might, well, let's see, once we learn the other ideas here, you might decide, nah, I'll just get it off the chart. You might find it quicker. But you feel like, hey, I've got this technology, I might as well use it. That's also fair enough. Now, the chart, also the way we do the calculator is going to be different here too. For area to the right, we're not going to be using that -1e to the 99. We're going to be using +1e to the 99. And I'm going to show you how to bring up that e to the 99 thing for on the calculator, which, the 83, they all have it. Now, I just shaded because it's going to be the same kind of logic. So I took a +z and a -z just to show you that it's the shading of area to the right, whether it's positive or negative. Let's see. Now, there's two ways you can do this. I know which way I like, but I'm not going to try to persuade you into well, you'll see as we go throughout some of the problems later, I'm going to do it the way I like. Now, we can use one of the properties of the normal distribution, the one that says the total area under the curve equals 1. So let's just say I wanted to find this first one. It's going to be the same idea for both of these, but I'll just pick the one on the left. And I want that area to the right. If I look up the value on the table for whatever that z is, that is not going to give me what I want. That value always reports back the data to the left. So it would be giving me this empty portion under the curve. That's what the chart would give me, but I want the red part. Well, okay, since the entire area adds up to 1, if I go 1 minus this empty part, that would leave us the part I wanted. So I can look up the value on the z on the chart, get that number. Now, when I say 1 minus, it means the table value, not the z value itself. I can look up, get that table value from the chart, and go 1 minus that number to get me the answer because of the idea of a complement. It has to add up to 1. So that way works. I'll show you that. And that works every time. Same thing if it's negative. You just look up the number, you go 1 minus that, and there you go. All righty. Now, the other way is using another property of the curve, the property of the symmetric feature of this curve. How you flip the graph over, like you look at this picture, you flip it over to the middle, it covers exactly the same on the other side. I got the picture. Let's get the pictures in with the description. Let's get the picture in here. You can use the fact that it's symmetric. So let's look at this. These zeros in the middle, so it's always symmetric across 0. That's key here. But if I wanted that area to the right of the positive z, because this graph could completely flip over to the other side, it would be the area to the left of negative z. Flip it over, perfect symmetry. So what that means is, what you can do, instead of this means you don't have to do the 1 minus. Without doing the 1 minus, all you got to do, so if you want, only if you're finding the area to the right, that's the key. Area to the right, if it's a positive z, look up the negative z on the chart and use that number as the answer. Don't do 1 minus or anything like that. Look up the opposite, that's your answer. Same thing here. Area to the right of a negative z by symmetry is exactly the same as the area to the left of its positive counterpart z there. So if I wanted the right of a negative z, I could just look up the positive z on the chart and I would have the answer. That's the second one. That keeps you from having to do the 1 minus. Now, I did this one both ways. Like I said, once we start doing kind of calculations and stuff, doing them both ways is pointless to do them both ways. And then, well, you're going to see calculator also too. So if that's going to be your route, that's fine too. But we know we'll certainly try them that way. But let's say this. So there's 3 ways for this one. Area to the right of negative 2.07. So I just made a rough sketch. The sketch isn't totally important by any means, but sometimes, and it doesn't have to be perfect, but sometimes it gives you a kind of visual there, you know, what kind of looks like. It doesn't have to be perfectly drawn, but at least, you know, I'll tell you what this sketch would tell me right off the bat. If I was looking, especially if I was looking at a multiple choice problem or something. So you see, I just put negative 2.07 just somewhere left of 0 and shaded it. All I do know is that graph is more than half of that graph. So I can, right off the bat, any answer less than 0.5 is certainly wrong. It would be automatically wrong for this picture. And that's very important if you were doing it by the first method. So if I said, okay, right of negative 2.07 means I can look at negative 2.07, then just go 1 minus that number. So to the chart. Okay, I figure I can start doing this a little bit quicker now. Right there. So there's negative 2.07, negative 2.0 row, 0.07 column, 0, 1, 9, 2. But you would have to go 1 minus this. So it'll be 9808. And when I design tests, I know I'm not the only one. A lot of instructors would do that because it's exactly the same thing. Is not only would I have the right answer there of 9808, I would have 0192 there as an answer choice. Just because that's part of the challenge of knowing that that's not the right answer, even though doing it this method, we used it to get that answer, but it wasn't the answer. But that all goes in with what I was saying about the picture telling me it's more than half the graph, and I would know that 0192 is going to be wrong anyway. Okay. Let's look at the symmetry method. So if I was finding the area right of negative 2.07, sort of like this number 2 looks like up here, all I have to do is look up positive 2.07 on the chart and watch what happens here. 2.0 row, 0.007, 9808. And that was the answer directly without doing 1 minus. I'm going to tell you that using the chart, if I was using the chart, that's the way that I prefer. But I'm not trying to influence you. If you like the 1 minus, go right ahead. Because it's nice sometimes, you know, we're just all about doing it whatever correct way is to get the right answer. Because sometimes in like mathematical stuff, you don't always have multiple ways to do things, you know. So, but this one is, and hey, I'm all about getting it correct here. So, and let me show you the calculator. Oh, looks like I kind of saved the keystroke deal there or whatever, but I'll type it in there directly. Now, look how I wrote that. This is important when it's greater than. This is how greater than in interval notation is always written as whatever the number is first, negative or positive, doesn't matter, comma, positive infinity. So that's just going back to algebra. You know, less than always starts, because people will mess this up. You know, that's why they'll ask me, why am I not getting this right? Less than, you start with negative infinity and then finish with whatever your number is. Greater than, you start with your number and you finish with positive infinity, which, you know, you could use like 100 or something like that. But I'll use 1e to the 99 here. That way I can show everybody how to enter it. And once again, if you're typing this in with an 83, you do not need to put the 0 and the 1 there. Okay. All right, so we would go. So very important that we structure the order of entry here, because now, yeah, I don't want that. I'll put negative 2.07. But if you wanted to do 100 here, you could. But I want everybody to see how to get that 1e to the 99. It's not hard, but I want everybody to see it. But yeah, if you put 100 in here, you'd get the right answer. So you go to 1, and you go second, right up there, and the comma. Now, above that comma, it shows EE, but it only prints out E. That's okay. Don't ask me why. I don't know. But that's the right command. Second, comma to get EE. That brings you your E. Then I just type in the 99. I can leave the 0 and the 1 there. So any of the TI, you know, you can just do the negative 1e to the 99 or 1e. Now, just let me remind you that when you do the negative 1e to the 99, or anytime you enter a negative number in the calculator, you use the minus that's right here beside the enter stroke, your enter button. Don't use the subtraction thing. Okay. 9808, which we know that's the answer. So you kind of got some options here. It's funny in the past, you know, not necessarily for this or whatever, but it's sometimes things like this in math, but usually it's in statistics or whatever, when there's more than one way to do something. Somebody will fuss at me. They don't want the options. They'll just say, tell me one way to do it, you know, but I can't do it without showing you the options. You know, some people want to be regimented about their math and just, you know, no, just one way. I want to learn one way. But yeah, you can choose one way yourself, but I got to show you all of those. You know, I'd feel guilty if I didn't. But it's just funny when somebody just kind of fusses at me like that. Let's see. Now, this one won't be as tricky if you're using the chart as the last one was, I don't think. And it certainly will be easy in the calculator too. But the way you do it whenever it's between two values, it makes no difference whether they're negative or positive. Like this one, I just happened to do an example with both being negative. One could have been negative, one could have been positive. They could have both been positive. It just means that the area is between the two numbers, not less than, not greater than. It's a real straightforward calculation. You don't have to worry about, you know, doing 1 minuses or anything like that. What you do is you look up the two Z values on the chart. Don't change either one of them to negative or positive, none of that. Just look them up as is, and you subtract the larger minus the smaller one. Because remember, the answer's got to be between 0 and 1. So it doesn't matter which way order you look it up, just make sure you subtract it or just know that the answer has to be positive. So this is saying between negative 2.16 and negative 1.35. So I don't need, I just kind of drew a rough sketch here, but I don't really need the picture for this one. I'm going to go to negative 1.35. All right, it's right there. That's the 0.05 column. Now you might be looking at me. Obviously, you'll be looking at the whole chart, but if you're looking at this now, you might be going, hey, dude, that's the sixth column. It is the sixth column. That's because the first one's 0.00. That means if you didn't have a second decimal place. So, but obviously, you don't have to do it this way. You'll be able to look at the whole thing. But I've had people ask me that before. But hey, they're assuming 1 is the first column, but actually 00 is the first column. So that doesn't happen too often. But so there it is, 0.885, and the other one was negative 2.16, I think. Let me double check. Yeah. That'll be this column, 0.154. So then I put the larger one first, the smaller one second, and then subtracted. But like I said, if you subtract in the wrong order, just know you have to make the answer be positive. I've been known to do this sometimes on a test, is have the right answer and then have the negative of the right answer there or whatever. But yeah, but the point is negative is not even an option. Z-scores can be negative, but probabilities can't be negative. Area can't be negative. So just, so if you get them in the wrong order, subtract them, make them positive. Now, normal CDF, we don't need the 1e to the 99 at all, or negative 1e, because we're not using either infinity. So it's just lower number, upper number. I believe if you put the wrong order of the numbers, I think it gives you the negative of the right answer. You can try that yourself if you wanted to. You don't need to, but once again, you just have to know it's positive. Negative 2.16 and negative 1.35. Should have known that. 0.731. Yeah, okay, here's just kind of a weird one. This won't really come up in the context of like a word problem will do or anything like that, but I guess it is possible I could put this as a, look at this picture and find the area basically or whatever. So you're trying to find the total shaded area. So you just have to do, well, there's another way. I can mention another way to do it, but once again, I don't know if I need to or not, but there's another way you can do it. Maybe I should tell you now that I told you that, but let's look at the kind of primary way to do this, certainly, is you just treat them as two separate pieces and add them together. That's easy enough. So if you do it by chart, you would look up negative 1.47 to get that left area, 0.708. And then to do right of 0.68, it's either the 1 minus way or the one way I told you about flipping it over and change the sign. So if I got a 0.708 and a negative 0.68, it's 2483. Actually, I think I'll show you the other way in the calculator. I'll just show it to you instead of writing it down even. And you add those together and that would be your answer. And here's how I did normal CDF. Now notice with normal, the flipping it over, flipping over the signs, that's only if you're using the chart. And the calculator, as long as you do the correct interval notation, you don't have to change anything. Lower to upper, yeah, that's only for the calculator, the chart purposes. So I went from 0.68 to positive infinity, and that got the 2483. Add those together. But the other way you could do it is, you could do the 1 minus the middle area, and that would use the skill we just learned. So I could do 1 minus the middle. So once again, I'm probably putting too much stuff in your head. You don't need to, well, actually, let me clear all this. I'll just do the 1 minus first so I don't already forget. What are the two numbers? I gotta go back and check them. I can't remember anything. Negative 1.47 and 0.68. I don't have to put the 0 there. That's okay. So we're basically, that's finding that. So this normal CDF is doing the empty part in the middle. It's doing the empty part. And since all of it has to add up to 1, 1 minus the empty part would equal those two shaded parts added together. $3190. Okay, don't panic. I told you this could happen. It's, you might be off on that last decimal place just a little bit. But I don't think that's going to cause you any problems in the homework, because I think it's kind of a built-in, tolerance for a little bit off on that last decimal. So yeah, okay, 3-1, but that was correct. So, all right, about time for break here. I'm going to look at the homework for a second, though. If I remember, maybe I'm thinking wrong, but I'm thinking that these first two might be combined together in one homework, so maybe it might be worth it waiting till after the next part. But I'll look and see first. If there's anything designated just to this, then we can do it real quick. All right, I'm just going to kind of leave this here and just tell you. Okay, now you'll see this in the next section anyway. But now this phrasing, now they're phrasing in as probabilities, which is what we're going to be doing here in the next section. So that probability would be the area left of 0.45. This probability would be the area to the right of negative 1.85. There's my sketch there. So that probability means the area between those two. So now we're getting in the idea of, just instead of using the word, instead of saying finding the area, we're now starting to use the phrase find the probability, but we're still doing the same thing. We're still finding the area. All right, so let me bring in my math lab here and see. I don't know, maybe I'm thinking it wrong. I don't know. Because if it was going to, if each problem was going to have combined parts to it, it might be easier just to wait till after the next section. But I don't know. I could be thinking about a different section. I won't know till we get there, till I look at this. All righty. Let's see what we got going here. Oh, now I know. Yeah, now I know what I'm thinking. Yeah, okay. Yeah, now it's coming to me. Even though I've broken the, I think I'll still look at it here real quick, but I've broken the, just for ease, because the normal distribution is a lot of material. So instead of making it one gigantic section, I just kind of break it into pieces. But most books do it as one gigantic section. So we do have this, but we'll still do it, even if we won't worry about part 3 today. But let me just look in, and that's what it is. It's not separated in the homework. But maybe there's one I can do that only relates to what we just learned and doesn't include anything else. But we don't need to spend a lot of time on that. It's the next section we need to spend a little more. Yeah, okay, this looks like, let me just check this. This looks like one we can do real quick. Oh, okay, that's kind of similar. Let me just look ahead real quick. I can do that one, then we'll go on break. I wonder if I'm wrong about the probability of x equals something if it turns up in this homework or not. I'm just kind of looking ahead. So maybe that's not in any of these problems. But on some of these, we won't be able to finish them because part D on these later problems is going to be from the part 3 in the notes. So I think this thing is slow. Okay, maybe I thought there was going to be one where it said the probability that maybe the problems are different now of X equaling something, and that's the one you were going to automatically put 0. Okay, so I guess that's not happening for these after all. Okay, I wanted to warn you about that, but it looks like that's not showing up anywhere. Maybe, but it has before, I know that. So I would just tell everybody just to put 0 and go about their way. So let's do that first one real quick. I may not even write these down. I might, if it's okay, I don't know. You want me just, I can do them in the calculator real quick, or I can verbalize the chart while doing them in the calculator. I can do both at once here. Let's do number 1, then we'll take a break and cover the next material. Less than 1.52. Oh, I guess I should take these off so we can actually get the check mark ourselves, right? Less than 1.57. I could get that real easily off the chart or the calculator. I'm quicker on the chart, but I don't know what to do here. What's best for you? That's all I care about, what you want to see. Because it could easily be, on the chart, you just look up 1.57. That's easy. Calculator, you would do, because this kind of has a sort of a mix for people, because this is, obviously sometimes the calculator really benefits you. But this might have a mixed feelings thing here, mixed opinion, I should say, of which way you're going to want to do it. Because you might say, nah, I'd rather do that, something like that off the chart. And it would make sense, actually. But I'll just do it in the calculator real quick. And hopefully if you're using the chart, see if you get my answer, if you're playing along with me here. That you can check yourself. I'm going to go 9418. So that's what you should see in the chart. Greater than 1.89. All right, I'm not even going to worry about the 1 minus 1. I'm just going to tell you, if you're doing the chart, look up negative 1.89. Because that's the one with the symmetry and the flipping over. Look up negative 1.89. I'm going to do it, but see, I don't have to do negative here. Well, I could, actually. It's up to you, but since I already had this negative 1e to the 99 there, it is tempting to put negative 1.89 there instead of doing it. But you could have done, I feel like I'm shortcutting this on you here. You might want to see it the other way, huh? I'll tell you what I'll do. I'll tell you what I'll make up for that here in a minute. 0294. Fantastic. All right, I feel like I did cheat you out of that, so I'm going to show you this one. I'm feeling guilt here. Oh, I don't want that. That shade norm actually just sketches pictures of the normal graph. I'll do it as 1.89 lower, and then, because you don't have to flip it for this, 1 second EE. So now I'm doing it in its original written form, starting at 1.89 and going to positive infinity. And look at the answer, same answer. But I was tempted, I left it that other way just because I already knew I had that negative 1e to the 99 in there already. So I made it easier to type that back on there. All right, so we're tearing this up here, aren't we? Between 1.57 and 1.89. If you're using the chart, We just did that. Look up 1.89, look up 1.57, and subtract the two results, and make sure you subtract it and get positive as the answer. And the calculator, I can just know I don't need any 1E to the 99s here. I just need 1.57 and 1.89. Zero, 2, 8, 8. Look at us go. We don't almost know what we're doing here. Now let me tell you a little trick for this one when you do it yourself. This happens to coincidentally work out. I'm glad I did that other, maybe that's why I did that other problem with the shading at two ends, not so much for test purposes, but because it came up in the homework. well, either way, I did it, so that's good. This last question is like this one. Now, and I'm also glad I showed you where it was, treated as 1 minus the middle part. Well, let's go back. We can make this real quick and easy because, let's see. Wait. Oh, there's two ways. Yes, two ways you can do this. Less than 1.57 and greater than 1.89 only because of the same numbers. I can add these two numbers together. That will be correct. Or since we just found the middle, I can do 1 minus that number and it's going to be correct. Watch this. If I go 1 minus and then go 9. Now once again, it could be off due to rounding. And I'll add the 0.294, but it might work. Ta-da! How about that? You got two choices. So they designed that problem where it would work out that way. 9712. Check answer. Come on. Well done. Perfect. Perfect time to stop. My computer clock says 8:19. And I say we go with 8:30 restart here. That sound like that? Okay. Kind of what we've usually been doing. That seems to work out well. I'll go ahead and bring these notes up. You just kind of want to look at them or something. Well, I guess you can look at it from your own point of view too. And let me just double check to make sure there wasn't anything in the chat or anything. So, all right, terrific. 10-minute break it is. All right, welcome back to the show. As you could probably tell there, I was looking around. We'll talk about it toward the end, but just kind of looking at what was uncomfortable. Sort of kind of mapping out the progress of the rest of the course. We're doing okay. I'd like to have an extra, it'd be nice not to have that freeze week, but get a little congested around exam 3, but we're easily going to be able to cover all the content during the lecture periods. We'll worry about the exam 3. Let's get exam 2 out of the way first. So let's finish this and we'll have a brief discussion, when this is over, what we're going to do. All right, regarding the exam 2. Normal distribution part 2. Let's let the games begin here. Looks like I'm kind of talking just a little bit more about the calculator here. Okay, I talked about that in the last section, but here it is again. And I guess I just didn't formally, maybe this should have been, I should have put this in the last section, but well, whatever. What's done is done. We're covering it either way. So, but we'll be able to get through this a lot quicker because I think I recently added these to the notes last semester for the first time. So it got more detail with the calculator stuff. So you just see I have less than, you got to go negative infinity to 10, greater than 50 to infinity, and then between two numbers. Oh, and here's how I'm explaining the commands. I already showed you this, and you'll see it again, but I'm just sort of that way people can go back and see it in writing. They don't have to like go through the lecture if they don't want to find it. But I'm just showing you the detail on the -1e to the 99 and the 1e to the 99. Okay. And I won't read all that verbatim, but so it looks like it's telling you then when it's less than, it starts with a -1e to the 99. Okay. But what is going to be a little different this time is I'll show you a couple of different ways to do these problems, but some of them are going to involve using typing in the mean and standard deviation that are given to us in a problem. So we'll get beyond the fact of just using 0 and 1. But anytime it's just z's, you don't need the calculator. Just the 0 and the 1 don't have to be there. So now normally distributed, or the problem might say it's not trying to trick you or whatever. It'll just say assumed to be normally distributed. That kind of goes back what I was showing early in the lecture about it might not be exactly normally distributed. Where was that thing? But we're going to say that close enough for government work here. That okay, assume it's or approximately normally distributed. It may use that phrase. Don't that changes nothing. In your mind, that's still normally distributed. It's not a trick or anything. So now we're going to take data sets that have means and standard deviations. So we got a business. It's a light bulb. Lifetime of these light bulbs. Suppose they've tested thousands and thousands of them, so they're just going to kind of use this as the population mean and standard deviation, even though it's probably not for every light bulb, but close enough. And we've come to the conclusion that the mean is 200 hours. Standard deviation is 40. Okay. All right. So it says find the probability that the bulb selected lasts more than 250 hours. Okay. Now, because these are not just straight up Z's like they were in the last section, and obviously I'm not going to be looking at you how you write this out, but I just want you to kind of understand, what I'm doing. It's good for you too. So, I write this as an X because technically we're dealing with an X because remember, it's only a Z whenever it's mean 0 and standard deviation 1. But we talked about last section, we know how to easily convert it to a Z is using that little formula right there. And of course, we have to and I'm not going to get tricky on the wording or anything, but you're obviously going to understand that more than means greater than. So obviously, now you have to be careful going back to the discrete distributions, whether we say more than or, at least, that makes a difference because of whether it includes the equal. But here, all we have to do is get the general direction. So it's kind of weird that if you accidentally did put the equal below this for the normal distribution, it would cause no harm whatsoever. But it would cause a lot of harm in a discrete distribution. But here it makes no difference. We just have to know it's going to the right. So what I'm doing right here is I'm just converting this over to a Z. So I'm taking the X values given to us in our problems, 250. Minus the mean of 200, and then divide by 40. And I got 1.25 as my Z. Now, on these Z's, if you're using the chart, you round these to 2 decimal places because the chart only shows 2 decimal places. So that's where it sometimes can be a little bit inaccurate when you do it versus the, but I think the homework seemed to have been set to where that it'll accept the answer for chart or calculator, even though if they're a little bit off, which they can be sometimes off by even more than just 1 on that last decimal place. But anyway, if you're using the chart greater than, I just drew a little sketch. I wrote what it was in terms of X, and then right below it means what it is in terms of Z. And greater than 1.25, if you use the chart, would be the same thing as less than negative 1.25. All right, where's my chart? I don't know where chart. I hate when I can't figure out where stuff goes. I should just bring it up as a separate PDF file so that way I won't lose track of it. And this thing at the top of the screen makes it hard for me to see. Oh, there it is. Now I know where it is. So I'll look up negative 1.25. 1056. And then as a percentage, every once in a while my question might ask the answer in percent form, but like even on a test, but that's not difficult. You just take, the decimal, multiply it by 100 or move the decimal over 2 places. So we're from a probability standpoint, so that's your area, which area is probability. The area is 1056. As a probability result, what we're saying is that you've got a 10.56% chance that you pick out a light bulb that just happens to last more than 250 hours. And you got an extra good one there. All right. Now in the calculator, I won't retype this one. You're going to see me type in, just to save time. You're going to see me do new ones in the homework here in a little bit. So I'll just explain what I've done with these. So this is a little bit different. Now this is if you're using the chart. If you want to do this strictly in the calculator, you do not have to convert your X to a Z. You can do it strictly as X. So that's a little bit different because everything we did before was already a Z. So watch what I've done here. See, I'm just using everything and turning it with X. So 250 would be my lower number. Then that positive 1e to the 99 would be my positive infinity number. And then notice I'm actually putting in the mean and standard deviation that was given in the problem, the 200 and the 40. So on an 83, what you would have to do is do 250, comma 1e to the 99, and then you're going to need to manually type in comma 200, comma 40, which is not that overly difficult to do, obviously, but you will have to, whenever we're doing areas just in terms of Z and the TI-83, you can just cut off the parentheses because like I said earlier, the calculator defaults it as 0 and 1, but if it's anything other than that, you have to put it in there. And so long as you put, so what we did before still stands, but I also showed you that you can either not put 0 and 1 in there or the 0 and 1 can be there and it's still the same. So I put 200 and I put 240 and look what I got for the answer, 1056. So I like to show this though for people that are still using the chart way to do it. Using the chart way to do it, you've got to convert it over to Z first to do it. So like I said, I'm not trying to give you a sales pitch one way or the other here. So now the next one says between 180 and 210. So if you're doing the chart way, you'd convert both of them to Z's. 180 minus 200 divided by 40. 210 minus 200 divided by 40. I get negative 0.5 and I get positive 0.25. So we learned right toward the end of the last section of how to do between two numbers is you look up the upper number. So let me just tell you what, I didn't write them, but I'll tell you what these numbers are here. So if you look up positive 0.25 on the chart, I'll do it for you here real quick, because you got to be careful. Positive 0.25. It's 5987. And then the other one was, oh, wrong notes. Negative 0.5. So negative 0.5. And when there's no second decimal place, it just means, negative 0.50. So it'll be that first column, 3085. So you subtract those two in the larger minus smaller order, and you get 2902. Now, the reason I mention that, for someone using the chart, I used to work in the 9th floor tutoring lab downtown for several years. And as so you're working with people, you see what kind of mistakes, you learn directly what they're seeing, kind of, and they'd be doing these homework problems while they're in there, and sometimes it'd be something like it was supposed to be 0.25, and they were looking up 2.5. So it's always kind of amusing. Like, oh, and then they get the answer right, you know. So it's kind of nice. I can see why they'd want to do their homework there with a tutor there, just so you hate to be agonizing over a simple little mistake like that for too long. But yeah, so I've seen that happen. So just watch for that if you're doing it that way. If you're doing it in the calculator, who cares? You won't have to worry about that. So here I put the lower of 180, the upper of 210, and then mean of 200 and standard deviation of 40. So you remember, whenever it's between two numbers, there's no infinity involved here. And look at that, 2902. I just drew a little picture there. Not important, but you can ask me if there's anything about the picture that you're interested in knowing there. But once again, I have what it is in terms of x on the top, and then converting to z is right below it. Dodge Durango, 18 miles per gallon, standard deviation 1.5 miles per gallon. What is the probability that a Durango selected at random gets more than 20 miles per gallon? And you see, it just says here, assume the mileage is normally distributed. That kind of needs to be thrown in there, obviously. So, well, the good news is, so let's just say there's, there was a big row of Durangos that just happened to have all the features and color and everything that you wanted. So it didn't really matter which one you picked. What would be the chance of this happening? So fortunately, that's good that this is a low standard deviation here, because if for something like car purchase like that, you wouldn't want that number to be too erratic. Yeah, that'd be great if you got an extra good one, wouldn't it? But you don't want it to also have the same equal risk of getting an extra bad mileage one either. So a low standard deviation kind of means it's not going to be a lot of fluctuation. Now, of course, sometimes the mileage they actually tell you it's going to be is not correct. But I'm just talking about what it really would be. It should be consistent if it has a low standard deviation. All right. So it's more than means greater than. So if you were converting it to a z, you'd do 20 minus 18 divided by 1.5. And that's actually like 1.333333 or whatever, but you just round it to 1.33. I'm choosing, because it's greater than, I could have done 1 minus, but I'm choosing to flip it over and change the sign. So if it's greater than, you could go positive, make it negative. Greater than, if it's negative, it becomes positive. So I look up negative 1.33 on the chart, and be right there, negative 0.918. Okay. There it is in the calculator. You see, here's what I mean. It's a little bit off. But I think the homework will accept either one. And off in a sense, not that anything's being done wrong. It's because the doing it from the chart is we're taking 1.33, we're cutting it to 2 decimal places. The program and the calculator is treating it as if it was negative 1.333333. So the extra 3s there at the end is slightly making this different from 0.918 to 0.912. That's what it is. So that's the reason, is because of the rounding. Yeah, if the numbers divide perfectly, and then they're going to match up exactly. But whenever you have to round that second decimal place, these will be a little bit off. But it's not anything to be concerned about. I don't think it is in the homework. Certainly not on the exam. It's nothing. What I usually do is my answers are usually based on chart, because I never assume 100% of the people using the calculator. But once again, I make sure they're not super close together. So if you did in the calculator and got 0.912 and you did it correctly and you saw 0.918, you would then feel confident to choose that answer. But you just keep in mind knowing that, that's probably well, not probably, but it is the chart answer. That's exactly what it would be. All right, so don't let that bother you. Monthly water bills, mean 100, standard deviation 12. A water bill is randomly selected. Find the probability that a selected bill at random is less than 80. All right, less than. Once again, no tricky wording here. Less than means less than. And so you convert it to a z, you take the 80 minus the given mean. The mean standard deviation will always be given. So will the number you're calculating, of course. 80 minus 100 divided by 12. And this is probably another rounded one here. Less than negative 1.67. So, okay, remember that this is less than. So you don't, if you're using the chart, don't do anything to the chart. Sometimes people, when they're doing this the chart way, and that's the only way that they're learning it, sometimes they get excited about wanting to change that sign, you know, from negative to positive. But that's only when it's greater than. When it's less than, that's it. You go right to the value on the chart. So I'll skip the looking up the negative 1.67. You can double check for me, obviously, but it'll be 0.475. And that would have been negative 1.666666. So it rounds to negative 1.67. All right. Okie doke. And come down here. And there it is in the normal CDF. Negative infinity, comma 80, because it was less than 80. The mean is 100, and standard deviation is 12. And there it is, 0, okay, slightly off, but no concern. 0.478. That's okay. I've already explained why that's happening. Between 95 and 128. So if you were converting both of these, if you're doing it by chart, you got to convert both of them to z's. So you do it like converting both to z's, you get negative 0.42 rounded, 2.33 rounded. So you look up 2.33, which will be 9901, and negative 0.42 will be 3372. You subtract those, so you get 6529 doing it the chart way. All right. But in the calculator way, it's pretty straightforward. Just put in negative 95 as your lower, 128 as your upper, 100 mean, 12 standard deviation. But like I said, this one's off even more, probably because of you had rounding at both ends, you know, so that made it off even a little bit more. Well, and I guess you can argue that the chart one is the one that's off actually, but hey, well, whatever, you know what I mean. 6517 versus 6529, but it's nothing to do with, it's just a more accurate process than the calculator. Same data, more than 138. So greater than 138, so it'll be 138 minus 100 over 12, greater than 3.17. If you're using the chart, you could easily flip it over and look up negative 3.17, which will be 0.008. And you see down here in the calculator, so I went 138 to positive infinity, which is 1e99, same 112. That's just scientific notation. I think we mentioned that during the binomials stuff when that comes up. If you move that over 4 decimal places, 1, 2, 3, 4, you'll have 0.00077, which would be the same as 0.008. So don't let the scientific notation scare you. More than 85, convert it to a z again, you get negative 1.25. This one, if you flip it over and use the chart, you'll look up 1.25, which is 8944. And then doing it this way, we get 85, 1e to the 99, then the 112 again. There's, okay, 8944, there it is. So, all right. And here's how I'm explaining about the answers not matching and everything should be okay. But on a test, it's probably going to be the chart answer. That's all this is saying. Oh, this is one I usually don't save the notes on, and I'll let you read that. If you have any questions about it, you can ask me later. I believe that's all it is. I'm just summarizing. I'm mentioning the stat lab, but we'll accept either answer. Okay. This one. So this is just like to have like a fresh, because we're going to have fresh problems when we do the homework here in a minute, but I like to have a fresh problem in the notes too. And I'll do this one in the calculator also. But I'll set it up as if it was all right, so the mean and standard deviation, mean's going to be 49 minutes. Standard deviation is 16. Don't make that the same as the answer. All right. Probability that a person selected at random will be more than 60 minutes. Okay, so if you're doing it this way, you convert it to a Z. I don't know if anybody's doing it this way that's actually listening to this, but if they are, people watching this later might be, so I need to at least be polite. Oh, I see it. Don't tell me. 16 on the bottom. All right. But people watching this later might be using the calculator, the chart, so got to make it fair for everybody. That's just going to be 11 divided by 16. .6875, so I'm just going to round that to 0.69. And because it's greater than, I'm going to do the flip-flop. I'll put the 0 in front, I guess, now, but I didn't have to. And then for those of you, I'm just kind of skipping the chart process right now, but so now you just look up negative 0.69 and you're going to get 2451. That chart value will be this answer right here. So in the calculator, we can go, all right. It was greater than, so I'll go 60. And I'll go 1 e to the 99. Mean, I know standard deviation 16. 49, 49. Standard deviation 16. All right, so I'll let you look at that for a second. And 2459. Like I said, a little bit off due to rounding, but that's okay. That was solved correctly by us both ways. All right. Now let's see what we got here. Oh, it looks like I have an extra page in there. Almost done. Get rid of that page. Suppose that SAT math scores are normally distributed with a mean of 518 and a standard deviation of 115. Now, the way this question is being asked is what percent of the math scores are less than 500. That's calculated exactly the same way as if you were just saying what's the probability that one person is less than 500. That's calculated the exact same way. So it's strictly a probability that any one of them is less than 500, then would also represent the percentage of all of them that are less than 500. All right, so less than, we'd take 500 minus 518 divided by 115, and that gives you negative 0.16. So as I mentioned earlier, be careful if you're using the chart. that you look up negative 0.16 and not negative 1.6. So if you look up negative 0.16, you'll see 4364. And then as a percentage, that's 43.64%. So you're expecting that percentage of the scores to be less than 500. All right, now let's look at part B. Now suppose if 1,500 SAT math scores are selected, about how many would you expect to be less than 500? And how many would you predict to be less than 500 based on that many, and then knowing the percentage we're expecting to be less than 500 and 1,500 people took the test. Now, this is the calculation for this is very easy. And it's similar to an idea that we had on exam 1. There was a problem that had a pie chart that had different percentages. Forgot what it was. But anyway, then it asked you, out of so many, how many would you expect to be of a certain group? And you had to pick the right percentage off the pie chart. So I can't remember what the story of the problem was about, but I want to say one time I know I did it was like people living in apartments versus blah, blah, blah. I don't know what this one was. But anyway, all you had to do was multiply the percentage times the total. It was easy. And that's the exact same thing you do here. You multiply the percentage times the total. Of course, these answers have to be whole numbers. You just round to the nearest whole number. We don't have to worry about rounding up or anything like that. Of course, the percentage needs to be back as a decimal. So all you do is take 1,500 times 4364, and that's 655. It's a little higher here because of rounding again. Because if you do your probability, and mentioning if you do the probability using the calculator for this example, you get 4378 instead of 4364, so that slightly alters that a little bit. But obviously, with that, I would account for that on an exam, and once again, by making sure that both of those are not answers, in other words. So you could then go by the rule of picking the closest one. All right. So, okay. Now, the last thing that's actually in this section is, and before we go to the homework, and I mentioned this sort of casually earlier, but if your z-value goes kind of off the chart, you could use, the smallest one R shows is 002, but you could use 0001, or you could probably even use 0 and be okay. And same thing with the upper, you might be, if somebody's using the chart, that number's not on the chart. Like here's one where, I actually did these in the calculator. Now these are Z's. Oh, okay, this is using the negative 100 once again because it was the old way I used to do it. But instead of the negative 1e to the 99, but I promise you it's the same thing. But look at that number, 4.06, 10 to the negative. That's 10 zeros in front of that number. So you could pretty much use 0 and you'd be all right. Now this one isn't exactly 1. Mathematically, it's not exactly 1, but it's super close to 1 that the calculator probably just rounded it to 1 because it just didn't want to print out enough. I guess I didn't really want to do a scientific notation on the positive end like it does on the negative end. So instead of putting a bunch of 0.9999s there, I just used 1. That's not going to make much difference. So, all right, let's jump back into the homework here. Playing around with that a little bit, and that could be the end of our day. How sad indeed, huh? I know you're devastated. Hopefully it didn't log me out here. All right, I'll probably skip this one. It looks like, let me just check all the problems. Let me just give you a little guidance here on part C, a little verbal guidance on this one. that less than 0.22 or greater than the mean, that's going to be one of those ones that has two separate shadings like we talked about earlier. But, greater than the mean actually means greater than 0 for a standard normal curve. But you don't have to even put that much thought into it. Because the mean is right in the middle and the total area of the curve is 1, that means the area greater than the mean would be 0.5 and the area less than the mean would be 0.5. So really all you would have to do for part C is just calculate the area less than negative 0.22 via chart or calculator, then just add in 0.5 to the answer. Now let me do the negative point. I'll do it in the chart. So I'll look up negative 0.22. Yes, it's 4129. If I add 0.5 to that, that's going to be 9129, which is what the answer was. I won't use that kind of trickery on an exam or anything, really, or not whatever, but yeah, so you just look that up and then just add 0.5, like I just explained, 0.5 will be the area to the right. So it's just, that's a little weird. We hadn't talked about something like that specifically. And part D should be pretty straightforward. We've done that, less than or the greater than, something that just didn't say the mean like that. All right, so you should be okay with D. So let's move on and start doing some of these application problems. But here's where we run into a problem is a lot of these, the part Ds. So that you keep this in mind if you start tackling. The good news is you can always do it and then do an unfinished problem. But I want to verbally tell you that if you start working on some of these, I mean, if you self-study the material, that's up to you. But I'm just saying, and what do I do on part D? The part D's on this one, I can tell you that part D on number 3 is the part 3 of normal distribution that we're going to cover next week. So it would be right for you to be confused by that. So if you want to tackle some of these, just do A, B, C and come back to D after we talk next week. Or if you're just dying of curiosity, you can sort of delve into it yourself. Let me look at the next one. I'll come back to this problem, but I just want to see. Yep, C on this one is, yeah, same thing. Not D, but C was, meaning next week stuff. So is C on that one, and D, I think, too. And then D on that last one. Yeah, so you'll have to leave some of those alone for now, but that's fine. Well, then you could do these and come back and knock those out. Let's go back and pick one. That first one was okay. The truck problem's good. So with this gallons of bottled water, this sounds fine. Let's put some new data in there, and we're just not going to do part D for now. Okay, let's see. Annual capita consumption is 30.7. I don't know why that's kind of a weird statement. Okay, they could have just, they put the same 30.27, 30.7 in there twice, in the description. They could have just said 30.7 one time. The mean is 30.7 and standard deviation's 11 gallons. Let's see. More than 36. Now, when I do the notes, I like to make sure I cover, obviously the chart way, then the calculator way. But when I start doing these, which obviously everybody's going to be able to see these too, but I kind of cater to the audience in this aspect. I mean, in other words, there's only a handful of you here. If you're gonna, if any, no pressure or whatever, but if you know you're doing this calculator, I'll just skip that part and show only the calculator. I guess if you want to say something meaning that you need to see it converted to a Z and set up to use the charts. If you need to see it, you can either say something or put something in the chart. And I think so what I'll do, if you abstain, I'll assume that I can just show you the calculator. So I'll give you a second here. Obviously, you can still chime in and whatever after I start doing this, because I could go back and do after I started doing the calculator, I can go back and do it the other way. So I'll just let you respond that way, so you don't have to all just yell in, calculator or chart. So we'll go calculator, but if you want to see the chart for what we can. More than 36. Okay. Second distribution. It's kind of nice to get some extra worth out of these calculators, right? Extra good use out of them, other than just basic stuff. All right. What's our lower? 36. And we're going lower to upper. So 36. So we just happen to, obviously it's going to leave in there with whatever you had before. So we just happen to have an upper there. So we were already set there. The mean and standard deviation is, I should have memorized those, 30.7 I remember, but 11 standard deviation, 11. And then the nice thing about this is for each part of the problem we do on this, it'll retain the mean and standard deviation for us. All we have to do is change the first two. So there's how you would enter it directly using the 83. I like 3150. Fantastic. Between 30 and 40. All right. So I can go second distribution, normal CDF again. It was 30 and 40. As I started talking, I forget. There. And you see the mean and standard deviation doesn't need to be changed until we get to a new problem. Bam! Enter. I like 3264. Yay. Less than 30. Less than 30 means we have to start with negative infinity. So it'll be negative 1. Yes, you have to start with negative infinity, and then 30 will be your upper. So sometimes people get a little confused. Hopefully, well, once you try it yourself, then you'll have it nailed, but sometimes people get a little confused at first with this. Four, 7, 4, 6. Excellent. And then part D we'll do next week. So yeah, obviously to do part D, I'll have to redo the entire problem, but obviously that's okay. We can see how quickly we can get through that anyway. Yes, I know. I want to leave it. Okay. This should be okay. This has a lot of parts to it, but it's okay. Looks like we got trucking company mean of 50,000 miles a year, standard deviation of 12,000. What proportion can be expected to travel between 36 and 50,000 miles per year? Okay. This is sort of like that thing I did with the SAT scores. Don't let that fool you. That's calculated the exact same way as if you were just asking the probability of one truck doing that. So that wording doesn't make it Now, I could have asked it as a percentage and we would have had to adjust the decimal, but proportion, you just treat it as the probability of any one fitting through there. So now because all the units, that's the key, is all the units are in thousands miles. 50,000, 12. If any one of them was different, I'd have to adjust my thinking here. 50, 36,000 miles. Anyway, I don't have to use thousands when I enter the data. I can just use the 36, the 50, and the 12, and it will be okay. But if something was a different, but if you rather put in the extra 3 zeros for your own peace of mind, it would not hurt my feelings in the least. But you actually do not need to do it. But that's only there. If something was different, you'd need to. If one was 1,000 and one was hundreds or something like that, let's see, 50 and 12. And the first one's between 36 and 50. Six, 50, 30 and 12, or 50 and 12. 50 and 12. Well, obviously we'll have proof whether, what I just said is accurate or not. I don't get the green check mark. Well, of course I could have missed it for other reasons, but so I just don't have the thousands there. Here's the moment of truth. 3783. Well done. Okay, now here's what it's doing this one in percentage. So we'd have to use it, we'll convert it to, so like if the last one was said percentage and it wants 2 places, we would have done 37.83 percentage. All right, this is interesting. It's less than 40 or more than 70. You can do those two calculations and add them together. Or we learned earlier, you can do 1 minus the middle amount between them. So I don't know what, from your perspective, what you're more comfortable doing. Or means add, but remember we had this, it was that one from the last section. It might have come up. Oh, and it came up in one of the homeworks too, where I mentioned you could just take 1 minus the between the two numbers. If you're comfortable doing that, I'll do it that way. It's less entries, but if you'd rather do it as individual and add them together, that's terrific. Nothing wrong with that. In fact, you could just do it as one straight plus calculation, because you don't need each individual piece. You could do the normal CDF, blah, 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 and hit the plus sign before you even hit enter. Maybe I should just show you that. And not have to add the numbers together separately. Here's what I'm showing about. So this will be the less than, so I need the -1, EE 99. The 50 and the 12 are the same. All right, I already forgot what that was. 40 and 70. See, notice I'm not going to hit enter here. I'm just going to put a plus sign and do the next one. Because I just want the sum of the two anyway. If not, I would have to get the two individual ones. And not that that's hard, but why get the two individual ones and add them together? Let's let it add together in one step. Now this one will start at 70 because it's the greater, more than, and it'll go to the positive 1e to the 99. Like I said, if you don't like doing the plus between the two, that's okay. I just figured this will be the final answer together right here, because they're separately added together. You might think, no, I want to see each one first and add it together. And guess what? That's okay. I got 0.2501, so I'm going to go 25.01%. Can't do part C. Yeah, I can do that. I'll tell you what, I'll do that number. That's what I'll do. I'll do the number 6, and don't let me forget. I'll do all of it from scratch since it'll be completely new. Some of the other ones I might just get to the new part only by using the given answers. All righty, an examination grade stats course, mean 73, standard deviation of 9. What is the probability that a student scored below 83? All right. Below is obviously less than, nothing tricky there. All right. Normal CDF, here we come. I need the -1e of the 99 first. I see it. And I got something so rattled I forgot all the numbers. 83, 73, and 9. Okay. I'm going to go 8, 6, 6, 7. Fantastic. Between 64 and 92. No problem. $64 upper, lower, excuse me. 92 upper. $8240. $8240. Excellent. All right. Okay. Here's where we go. Here's where we are. All righty. Let's stop for here.